All right, so we'll be looking at first, just note, so numbers 1 through 7 on that final exam review were covered in Saturday's Zoom meeting. And then number 19, 12, 13, and 14 were covered on Monday. So you can find those on the Zoom recordings. I can still go over them again if if somebody wants to. But for sake of time, I would kind of deprioritize those because you have already recordings with those being covered. This is the last final exam review session. So after this, you'll still have access to the recordings from these sessions as well as from those that were done in the first 8 weeks. Let's clear this off. All right, so you should be hearing audio right now. If you don't, check the volume level on your computer, make sure the volume is turned up, use the sound check link under the audio settings to test, or if you continue to have issues, call the Zoom tech support line. So you can, of course, ask questions throughout. You can raise your hand, use your microphone, or you can put in the chat. You can also use any of the different reactions. We will ask for feedback, but I also want to refer you to the live lecture schedule. That's the Google doc that has the links to the recordings from this 8 weeks, as well as if you go down through there, it tells even what questions were covered on those recordings. And you also have the recordings from the first 8 weeks. Now, you should also have the recordings from the first 8 weeks within your course somewhere in the modules. There's a module that has those. And if you look at those, they also list specifically what was covered in each recording. So I guess these don't all, but some of them do. So yeah. Those are additional resources you have. So we'll come back to the feedback link at the end. All right, so looking at this review, starting with number 9. And then the next one I'll do after number 9, if I don't get a request, will be number 17. All right, so number 9, we have a function. It is an exponential function, and we're going to look at the graph, the domain, range, asymptote, and y-intercept. So in general, an exponential graph is going to have a horizontal piece, and then it's going to turn and it's going to go up, and it's going to go up pretty steeply, but not quite vertically. That horizontal piece could be on the other side, depending on the base, but it's going to be that general principle of a horizontal piece, and then a sort of a turning point that turns it to going then close to vertical. You'll be using a graphing tool, so we won't see that here, but for the graphing tool, what you want to do is make sure you have the correct base, and then any transformations. So in this case, we would have the base of 6, and then the negative is going to be a horizontal reflection because it's changing x to negative x. So that would be a box you would check probably in the graphing tool to reflect horizontally. So that would change it from this form, that would be like the 6 to the x. When you reflect it horizontally, now it has the horizontal piece on the other side. And then the -5 here shifts it down 5. That would be a vertical shift. And that would move basically where that horizontal piece is. So the horizontal piece would now be at -5 instead of at 0. So you would have a graph looking something like this. It would have this horizontal piece basically at -5. It would really be slightly above. And then if you look at just to see where it crosses the y-axis, jumping ahead to the y-intercept, if you plug in 0 for x, we'd have 6 to the negative 0 minus 5. And that would be 6 to the 0 minus 5. Anything to the 0 power is 1. So it would be 1 minus 5, which would be negative 4. So we're starting to turn here to cross the y-axis at negative 4. And then it's pretty quickly going to get really steep. With the graphing tool, you're not worrying about specific ordered pairs or points on the graph. You're just applying the transformations. Sometimes the base will already be set for you. Sometimes you have to set it. And then any reflections, stretches, compressions, shifts would need to be applied. The domain for an exponential is always all real numbers. So that's not going to change. The range then is going to be from wherever that horizontal piece is. So we've shifted down 5. Normally it would be from 0 to infinity. Now it's going to be from negative 5 to infinity. And it's going to be with parentheses on the negative 5. So it never actually gets to negative 5, but it looks like it's pretty much there. The horizontal asymptote is going to be just the end point of the range. It's a horizontal line, so it's going to be y equals, and there's just going to be one of those. And then the y-intercept we found was negative 4. And pay attention, if it says type an integer or fraction, it just wants the number. It doesn't want the ordered pair. So that's number 9. The graphing tools, you'll see more, even if you look back at the recordings from the first 8 weeks. From module 7, you'll find examples of doing the graph with the graphing tool. All right, number 10, we're solving an exponential equation. So when you have an exponential equation, the first thing to look for, the easiest kind, is if you can rewrite both sides as a power of the same base. So we have 4 to the negative x equals 64. And if you recognize 64 is a power of 4, then you get 4 to the negative x equals 4 cubed. If you're not sure, and you think, well, maybe it's a power of 4, what you can do is take and start multiplying. 4 times 4 is 16, times another 4, oh, there's 64. Then you can be sure. If you get past 64 and you haven't hit it, then you know that it isn't a power of that base. You could potentially, if it was 4 to the negative x equals 32, for example, 32 isn't a power of 4, but they're both powers of 2. So if you can rewrite both sides as powers of the same base, then once you have that, then those bases cancel each other out. You can think of you're applying a log base 4 to both sides, undoing the base. And so you get negative x equals 3, and that would be x equals negative 3. You could also just apply a log base 4 to both sides. And so you would get negative x equals log base 4 of 64. If you don't recognize the 64 as a power of 4. But, all right, number 11 then, we have a log. A logarithm function, looking at various things related to the graph of that, of the function, as well as its inverse. So starting with the domain of any logarithm is you're going to take whatever is inside the log. So the log input has to be greater than 0. So in this case, we need the 3x to be greater than 0. The +1 part, that doesn't matter at all. That doesn't have anything to do with the domain. What we need is what's going into the log to be positive. So that becomes just x greater than 0. It doesn't want interval notation, so that would be parentheses 0 to infinity. All right, for the graph, So a log graph is always going to have the vertical piece, and then it's going to turn and be almost but not quite horizontal. The location of the vertical piece is going to be correspond to the end point of the domain. That's going to be also the vertical asymptote. So once you have the domain, then you just set x equal to that endpoint. If I have x greater than 0 for the domain, x equals 0 is the vertical asymptote. So that determines any like horizontal shifts. And then if there's a vertical shift, that's going to affect kind of where that turning point happens. It defaults to being around the origin or just below the origin. So if it's shifted, and in this case, we have the +1, so it's shifted up 1, we're going to have the turning point be a little bit higher relative to the origin. Now looking at these graphs, they all look pretty similar. So this is a bit tricky. You might have to, if you can't tell, start doing some calculations of, let's say I take 2 because it's counting by 2s. And, so each place, it's a little bit different at each of those. So if I plug in 2 for x, ln of 3 times 2 plus 1, ln of 6 plus 1, and then if I actually just go on the calculator, and that's 2.8 approximately. And again, keeping in mind, this is counting by 2s. So this would be 2. This one I could see is just below 3. So this is about halfway between 2 and 4. This one, B is less than 2. So that one is not there. C is also definitely less than 2. That one's no good. And then D looks like it's pretty much at 2. So that one's also, so A is the one. Typically it'll be a little bit more obvious if this was a shift, up 5, it would be pretty obvious which one was shifted up 5. Or, if you had a shift in different directions, a shift up versus a shift down, but these all seem to be just slight variations. So that one's a bit hard to identify the correct graph. But yeah, worst case scenario, you find a point where the same x value, you can tell that it's definitely different for each graph, then you can calculate what it should be and find whatever's closest. The range of a log is always all real numbers. That's something you just have to basically memorize and know. There's no calculations involved. Looking at the graph, it doesn't necessarily look like that because it really looks almost horizontal, but it does keep going up forever as well as going down forever. So that arrow to the right is also an arrow upward, even though it doesn't look like it. And the vertical asymptote, again, is just the endpoint of the domain. But you have, if the x equals isn't given to you, then you would have to type in the x equals. All right, so then we have the inverse. So we had ln of 3x plus 1. And 2 different ways to find the inverse of a function. One is you switch x and y and then solve for y. So we'd subtract 1 from both sides. Apply a base e on both sides to undo the log. So we would have then 3y equals e to the x minus 1. And then I'll just say multiply both sides by 1/3. So 1/3 e to the x minus 1 or e to the x minus 1 over 3. Method 2 is you think about the things that are done to x in order. So if you take an x, the first thing that happens is multiply by 3. And then the second thing that happens to that result is the natural log. And the third thing is adding 1. So we undo those in reverse order. So the reverse of step 3 gives the x minus 1. The reverse of step 2, the inverse of the natural log is a base e. So apply base e to that x minus 1. And then the reverse of step 1, instead of multiplying by 3, we divide by 3. So you get the same thing either way. It's just a matter of which process makes the most sense to you to get there. The domain and range of the inverse are just the domain of the inverse is the range of the function. Domain of any exponential is always all real numbers. The range of the inverse is the domain of the function. So 0 to infinity. And then for the graph, we want kind of the x and y have switched. So we have that horizontal piece at 0, but we had the point 2.8. So that was the x and the y. Then F inverse needs to have the switch of that. So 2.8 on the y, or on the x for 2 on the y. So we need again for the 2 on the y, we need to be about halfway between 2 and 4. And so that's that second graph is the one. The others are all a little bit too far to the left. All right, so that was number 11. And that's all that's been requested so far. I will say, I think I've never seen one of the graphs were that challenging to identify. So typically it will be more obvious which graph is which. They won't be that similar looking. But even if they are similar looking, you can also typically in MATLAB, you can click, there'll be a magnifier that you can zoom in and look closer at the graphs to get a better look at those details as well. So I'm going to look now at number 17. So what rate of interest compounded annually is required to double an investment in 19 years? All right, so compounded annually means it's going to use the p times 1 plus r to the t. It's really the p times 1 plus r over n to the nt with n equal to 1. So the n's kind of just go away. We're looking for r. We have 19 years, we have t. And then all we have for p is for p and the amount. By the way, this is on your formula sheet, so I'm gonna just real quick skip over to that. So on your formula sheet, you have the compound interest formula. So you don't have to have it memorized. You just need to know when to use it and how to use it. So all we know about P and A is we want to double in the 19 years. So you could either pick a value for P. Let's say we pick 1 for P, then we want to get to 2 for A. That's going to be the easiest. Or you could just say that A is 2p, and so you plug that in. But you end up then with 1 plus r to the 19th power equals 2. And then you would do, to isolate r, basically a 1/19th power or a 19th root to both sides. So we have 1 plus r, and then if I do 2 to the 1/19th power, that is 1.037, etc. And let me just adjust things a little bit here. All right. So that's 1 plus r. If I subtract off the 1, then r is just the 0, the 0.037, etc. But it does want the percent form rounded to 2 decimal places. So I multiply that by 100 or move the decimal 0.2 places and then round to 2 more digits. So 3.72 would be the percent form of that correctly rounded. All right. So next up, I'm going to do number, let's see, 20 is so much. I'll do number 16. Somebody asked 14. Okay, I'll do 14. All right. So number 14, solving this logarithmic equation. We don't have a lot of space here. I'm actually going to get myself some more space. Okay, so we have log 8x plus 7 equals 1 plus log x minus 3. Now, to solve a logarithmic equation, what you need to have is either a log of stuff equal to log of stuff. Then you can cancel out the logs. Or if you have log of stuff equal to a number, then whatever the base of the log, you would apply that base to both sides, and you would get the stuff that was inside the log equal to the base to that power. But if we have multiple things, we have the 1 plus the log, so we have to get it into one of those two forms, a log equal to a log, or a log equal to just a number. So I can actually do either with this. So one way I can do is if I get it to the log equal to a number, so I move the log of x minus 3. So I have log of 8x plus 7 minus log of x minus 3 equal to 1. Then I'm going to apply, I have these log properties here that let me, that I can use to combine logarithms. If I go from the left side to the right side, I have a log minus a log. I'm going to turn it into a single logarithm form. So this is going to be then log of 8x plus 7 over x minus 3 equals 1. And then you have to know when we have the log here with no base written, that is base 10. So I undo that log with a base 10, and I have 8x plus 7 over x minus 3 equals 10 to the 1 power, or just 10. And we'll come back to finishing solving that. But the other method if I use this property here in reverse, so I take the 1 and I rewrite it as log, and it's log base 10, then it would be log base 10 of 10 to the 1, or just log of 10. So that seems maybe sort of weird, but if you understand that you can do that, then I would have log of 8x plus 7 equals log 10 plus log x minus 3. Then I would use the product rule. So I have two logs being added together. I combine those by multiplying. So I would have then log 8x plus 7 equals log of 10 times x minus 3. Now that I have just log equal to log, I can cancel out the logs, and I have 8x plus 7 equals 10 times x minus 3, which would be pretty much the next step you would get to from the other method. So at this point, they've converged. Whichever method you use, you should end up, if you've done correct work, with 8x plus 7 equals 10 times x minus 3. And so that would be then 8x plus 7 equals 10x minus 30. And then 7 equals 2x minus 30. Add 30. Coming over here, 2x equals 37. So x equals 37 over 2. So that would be the solution set probably, but you do have to double check. So the last thing to do then is to test for extraneous solutions. You want to make sure that that answer isn't going to make the input of a log in the original equation be negative. So I double check. 37 over 2 is 18.5. Certainly if I'm multiplying it by a positive number and adding to it, that's fine. That's not going to be negative. And as long as it's bigger than 3, then taking it minus 3 isn't going to be negative. So that confirms that would be the solution. Okay, and you'll see that was done as well on Monday, and so you might get a different, somebody else's take on explaining it. It doesn't hurt to have more than one. We have seen that, so if you're still at all confused on that, you can look at Monday's recording and see if you get more out of that. But yeah, so that's number 14. Not seeing any new requests yet, so I'm going on then to let's see what I said. I was going to do number 16. Right, so this is solving an exponential equation, and again, I'm going to give myself more space with this. All right, so this is solving an exponential equation. But we have these two exponents and a number. And so what you have to recognize with this is you really have to recognize this is a quadratic form. And you have to do a little work to really see the quadratic in it. But if you recognize it, if you have an exponential equation that has an exponential plus another exponential and then a number equal to 0 to kind of tell that that needs to be a quadratic. So what I want to do first is rewrite the 4 as 2 squared. And I'm also going to note that the 2 times, or 2 to the x plus 1 power is 2 to the x times 2 to the 1. So that's 2 squared to the x. The 2 squared to the x, then that would be 2 to the 2x, or that could also be written as 2 to the x times 2, and that could be written as 2 to the x squared. And so I have 2 to the x squared plus 2 times 2 to the x minus 1. And now you can see maybe the quadratic in there. And I'm going to use u substitution. So instead of using 2 to the x, I'm going to treat that as an entire unit. So I'm going to replace 2 to the x with u just so I can focus on solving the quadratic. U squared plus 2u minus 1 equals 0. I don't think this is factors though. So let's, I'm going to use the quadratic formula here. So A is 1, B is 2, C is -1. So quadratic formula is on your formula sheet. You don't need to have it memorized. You just need to know how to use it. It's negative B plus or minus square root of B squared minus 4AC all over 2A. So -2 plus or minus square root of, this is going to be 4 plus 4 over 2. And I'm going to deal with the square root part separately. So that's square root of 8, which is square root of 4 times 2, which is square root of 4 times square root of 2. Square root of 4 is 2. So that's 2 square root of 2. So I have -2 plus or minus 2 square root of 2 over 2. Make sure that denominator, the 2 on the bottom, has to apply to both terms on the top. So it's -2 over 2 plus or minus the square root of 8 over 2, or 2 square root of 2 over 2, applying to both of those. So I end up with u is -1 plus or minus square root of 2. Now I go back to the 2 to the x power. So 2 to the x, instead of u, 2 to the x equals -1 plus square root of 2, or -1 minus square root of 2. Now, 2 to the x is always going to be positive, and square root of 2 is 1.4. So -1 plus square root of 2 works, but -1 minus square root of 2 would be negative. So that's not going to give a solution. But the -1 plus square root of 2 would. So I'm going to come up here for sake of space. So we have 2 to the x equals -1 plus square root of 2. And let's see, it says express irrational solutions in exact form. So it would be x equals log base 2 of -1 plus square root of 2. If it was just square root of 2, you could take log base 2 of square root of 2. But the -1 plus, we can't really do, we don't have any properties of dealing with addition inside of a logarithm. So we can't really split that up and do anything more with it. So this would be the exact value. So that's number 16, and I have number 18 requested. Right, so All right, I think I have everyone here, so I'll do it here. All right, so how many years will it take for an initial investment of $10,000 to grow to $35,000 if it's a rate of 11% compounded continuously? So first thing, when you see compounded continuously, is you need to know that that means you're going to use the A equals PE to the RT. That's on the formula sheet. You just, again, need to know when and how to use it. It does even say continuous interest, so you have that clue even on the formula sheet. All right, so then we have, so the initial investment you need to know is P, then what it grows to, that would be A. Interest rate L of 11% means R is going to be 0.11. You always use the decimal form of the rate. And then how many years I'm solving for T. So I can plug that all in. I have 10,000 e to the 0.11 t equaling 35,000. To solve this, I first need to isolate the exponent. So divide both sides by 10,000. And so I get e to the 0.11 t equals 3.5. If that doesn't come out when you do that division, if it doesn't come out to something that terminates, if it's a big long decimal, keep it in a fraction form. Don't do any rounding. So you don't want to do any rounding until the final answer on these. But in this case, it came out even. So then I can do a natural log ln on both sides to undo the e. So I have 0.11 t equals ln of 3.5, and then I can divide by the 0.11. So I'm going to take ln of 3.5, so 3.5 ln, divide that by 0.11. And so that's 11 point, what did it say? 2 decimal places, so 11.39 years. Right, and then I have number 15 being requested. So solving this exponential equation, and this is about as rough as the exponential equations get when you have different bases on each side. So I'm going to put this, give myself more room on this one. And we're looking for the exact answer. So, all right. So I have an exponent on both sides. Pretty much I have to undo the exponent. And there's actually various ways you can approach this. So I'm going to do about 3 different ways, and you can decide which one is the least or makes the most sense to you. You'll see they pretty much end up the same. But I can do a log base 5 on both sides. And so I end up with 1 minus 2x equals log base 5 of 3 to the x. I can apply the power rule to turn that exponent into multiplication. Then I need to get the x terms on one side. So I'm going to add 2x to both sides. So I have then, I'm going to switch sides. So x times log base 5 of 3 plus 2x equals 1. Factor out the x, so now I have x times log base 5 of 3 plus 2 equals 1. And then x equals 1 over log base 5 of 3 plus 2. So that's 1. That would be the exact value with one method. Another method is I can do a log base 3 on both sides. So in that case, now the right side would cancel, and the left side, I would use the power rule. And then I would need to distribute the log base 3 of 5. So I would have log base 3 of 5 minus 2x times log base 3 of 5. So distributing that to both terms equals x. And then I'm going to add the 2x times log base 3 of 5 to both sides so that the terms with x are together. And so I have log base 3 of 5 equal to x plus 2x log base 3 of 5. Factor out the x, that's x times 1 plus 2 log base 3 of 5. And then I divide, so I get x equals 1, or sorry, equals log base 3 of 5 over 1 plus 2 log base 3 of 5. That is also an exact value solution of that equation. Looks really different from the first one, but those are both, if you put them in the calculator and get the approximations, they'll come out the same. A third way is to just say, well, they're two different bases. I'm just going to pick, say, use a natural log. You could do this with a common log as well. And particularly if you needed the approximation and if your calculator doesn't do any base log, then you'd want to use the natural log or the common log. And I'm going to use natural log because it's 2 letters instead of 3. So I'm going to put an ln on both sides. And apply the power rule on both. So 1 minus 2x times ln 5 equals x times ln 3. I'm going to distribute on the left side. So I have then ln of 5 minus 2x times ln of 5 equals x times ln of 3. And then add the 2x ln 5 to both sides. So I get ln of 5 equals x ln 3 plus 2x ln 5. Factor out the x, so it's x times ln of 3 plus 2 ln of 5 equals ln of 5. So x then equals ln of 3 plus 2 ln of 5 over ln of 5. And that's another exact value form. And you can see there, and sorry, I did that wrong. Keep trying to divide in the wrong direction. Sorry, so it would be ln of 5 over ln of 3 plus 2 ln of 5. And you see there kind of you have the 1 and the 1 and the 2, which because they're ones, if they were something other than 1, you'd see those more strongly. But the if it's ln, it's ln of 5 base log base 3 of 5, or when it was log base 5 of, then it turned into 1. And then the ln of 3, when it was log base 3, turned into 1. When it was log base 5, was log base 5 of 3. And the 2 ln 5, or 2 log base 3 of 5, or just 2 when you used a base 5. So you can kind of maybe see how those relate to each other, just depending on the base of log that was used. So again, any of those 3 would be legitimate, correct, exact value answers. Hopefully, at least what you get out of this is that the ones where you only have the x in one position, in one power, are a lot easier. So let's go around time. All right, I'm going to do, I did number 16, did number 15. I'm going to do number 8. And then 20 if I don't get asked for anything else. So number 8 is dealing with inverse function. So we have 7 over 9 plus x. So first finding the inverse and then talking about the domain and range of the function and its inverse. I do have a request. I'll go ahead and finish this one. I think I have time to do this and that, but yeah, I can do that homework question. All right, so the inverse, we can either do, say, so we have y equals 7 over 9 plus x. I can rewrite that as x equals 7 over 9 plus y. That's the inverse, and then solve for y. So I multiply both sides by 9 plus y. Distribute, so 9x plus xy equals 7. Going to move the 9x over because I'm trying to isolate y. So xy equals 7 minus 9x. And then divide both sides by x. Y equals 7 minus 9x over x. Or that can be written as 7 over x minus 9. If you do the alternate method, that's a little tricky. The first thing being done to x is adding 9. Then it's put onto the bottom of the fraction. So that'd be a reciprocal. And then the third thing is multiplied by 7. So undoing those, we would divide by 7. And then undoing as a reciprocal is just a reciprocal. So flipping that to 7 over x. And then undoing the adding 9, subtract 9. And you have the 7 over x minus 9. So again, either of those methods you can do. So then we have the domain and range. So what you want to do is find the domain of each. So the domain of the original function, because it has 9 plus x on the bottom, x can't equal -9. The domain of the inverse, because we have x on the bottom, then the domain is x can't equal 0. So you can't have the denominator 0. So the domain of f is x not equal to -9. The domain of f inverse, x not equal to 0. Then the ranges are just going to be the domain of the opposite. So the domain of the inverse becomes the range of the function. If the inverse x can't equal 0, then in the function, y can't equal 0. And then we have x can't equal -9 in the function, so y can't equal -9 on the inverse. So that's the inverse. When you have the rational function, you can actually use the inverse of the rational function to find the range of that rational function. All right, let's see, we're asked for number, let's see, 8A homework number 43. All right, so using properties of logarithms to evaluate. So we have log base 3 of 15 minus log base 3 of 5. So neither 15 nor 5 is a power of 3, but we do have the log property, as you can see on the formula sheet, that when I have two logs being subtracted, that I can combine that into a single log and divide the inputs. So this would be rewritten as log base 3 of 15 divided by 5. Right? 15 divided by 5 is 3. So that would be now log base 3 of 3. And now I can apply another property from the formula sheet, which is log base b of b to the x equals x. So I just have to recognize 3 really is 3 to the 1 power. Then log base 3 of 3 to the 1 power is 1. Or I can also think of it as what log base 3 of 3 is saying is what power of 3 is 3. And so you recognize that that's 1. All right, so yours is different. All right, let's see, man. 8A, you said 8A homework. So yours is ln, let's see. More like this one, okay. Is that more like what you're talking about, I think? All right, so similar, all right, so this one we're expanding. So we're using the properties. So we have the property that log of m times n is log m plus log n. Log of m to the r is r log m, and log m over n. So those properties to expand. The one thing you have to recognize is square root. So square root is a 1/2 power. So I'm going to first rewrite as this is ln of x to the 13 times 7 minus x to the 1/2 power. Now I'm going to apply the product rule to split this into two logarithms. So it's ln of x to the 13 plus ln of 7 minus x to the 1/2 power. And then I apply the power rule to each to take those powers and move them out front. So it would be 13 ln x plus 1/2 ln of 7 minus x. But I would guess if you were getting stuck, most likely you were getting stuck on that square root being a 1/2 power. Is just a property of exponents that you're expected to know on these. All right. So hopefully that answered, you can apply that to your specific question. All right. Okay, so I looked at number 8. I think I'll wrap up by looking at number 20. Oops. Right. So this is radioactive decay. So we have a formula, a sub 0 e to the negative 0.0244 t. A sub 0 is the initial amount, which we're then told is 400. So that would be the a sub 0. The decay rate, that's what's the exponent there, but it wants the percent form. So the negative just means that it's decay. And then this 0.0244 would be 2.44%. Then they want to know how much is left after 10 years. So you would plug in the 400 e to the negative 0.0244 times t is 10. So you got to be careful putting that in your calculator a little bit. So I put the 400 and then I'm going to do e to the power. I'm going to put parentheses because I'm going to be multiplying two things in the power. And then I want to make sure and use the negative button, not the subtraction button. But I'm for this calculator, I have to put in the number first. So the 0.0244, then I apply the negative to it times 10. But make sure that you can do that correctly in whatever calculator you're going to be using. And this comes out 313.4. So round, it's round to the whole number, so 313. Then they want to know how many years to have 300 grams left. So I'm going to put 400 e to the negative 0.0244 t equals 300. Divide both sides by 400. E to the negative 0.0244 t equals, that would be 0.75. Again, if that didn't terminate, if it was like 400 over 300 and it was 1.3 repeated, you would just keep 4 over 3. But because it terminates, I can write the 0.75. Then I can do the ln of both sides, and negative 0.0244 t equals natural log of 0.75, and then divide by that rate. So I'm taking the natural log of 0.75 and then dividing that by 0.0244, negative 0.0244. And that comes out 11.79. So it rounds to the nearest tenth, so 11.8 years. And that kind of fits the previous question. It was 313 grams after 10 years, just a little bit more than 10 years to get down to 300. And then it asks for the half-life. So the half-life is going to be how long it takes to get to 200. So you're going to get 1/2 instead of 3/4, and it's going to have then ln of that divided. So just kind of following the same pattern as the previous calculation. Then let's see if I do 0.5, natural log of 0.5 divided by the 0.0244, 28.4 years. Half-life in general, you might see if you do it enough times, kind of see a pattern. It'll just confirm, like you can use the shortcut because it is always going to be that way. It's going to be natural log of 1/2 divided by whatever that rate is. But you can always just do the solving as well. So yeah, that's pretty much our time. And at this point, I think, if I've counted correctly, between what was done on Saturday and Monday and tonight, everything on this review PDF has been covered in one of these sessions. So you can go to those recordings and find those. But anything else anybody wants to look at or ask about before I end the meeting?